Hello, we are Team 3 and our project is based on the DCASE Challenge 5 for urban sound tagging with spatiotemporal context. Anyone who's lived in a densely populated urban environment can attest that the surroundings are noisy, which for many is a source of frustration and discomfort. An important step to mitigating urban noise, such as construction, shouting, and alarms, is to detect and identify it. But detecting such noises can be difficult, especially when the noise has an inconsistent form and is accompanied by lots of ambient sounds. To help inform the likely noise sources, we can try understanding the context in which the audio recording took place. Context is often described as information that informs us of the setting within an environment, such as the time of day, who's nearby, what they're doing, where this happened, and so on. And in this challenge, we specifically focus on spatiotemporal context, aka STC, which pertains to the when and where. So for example, music played by an ice cream truck would be likely at 3 p.m. on a Saturday, but much less so at 2 a.m. on a Monday. And STC as a timestamp and location can be used to query large open data sources to learn about events or trends in the city, such as nearby construction projects. And we took on a subset of this challenge in which we attempt to classify 8 general types of noise as shown to the right under the coarse columns. The sonic dataset contains 18,000 training samples and 1,000 testing samples, each composed of 10 seconds of audio collected from one of 50 audio sensors in Manhattan, Queens, and Brooklyn. An additional stipulation of the challenge is to use STC to better detect and classify types of noise by using the provided time and location annotations, in addition to any publicly hosted information related to the when and where. To use STC, we decided to develop a series of features using the STC time and location annotations as well as information queried from open data sources. We generated a handful of features based on the timestamp itself, in addition to features based on open data sources like OpenNYC and Pluto, including features for nearby construction activity, subway stations, city zoning type, and more.
Besides the STC features, we also generate some features directly from the audios after the short-term Fourier transform. Each audio is cut into 10-second pieces and multiplied with both short windows and long windows separately. Long windows provide less resolutions on time field but can show more details in frequency domains. Therefore, they may provide better results and thus commonly used. The log mail spectrum is generated after filter bank and log scales after SCFTs to decrease the dimensions and reduce the noise. The spectrum is implemented with the DCTs, and the first 13 dimensions are used as the well-known MFCC features. In addition, both MFCC and log-mail spectrums are averaged in time domains. The PCA and NMF are also carried out as another dimension reduction method. All data are normalized before the classification part. To solve this task, we applied several existing approaches on only audio features, as well as with STC features of the dataset. For each method and each group of features, we trained a binary classifiers of each of the 8 classes and evaluated them on the test data. All the machine learning algorithms that are widely used in sound event detections has been implemented, including the support vector machines, Gaussian mixture models, and hidden Markov models. Besides, we also tried other classifiers such as logistic regressions and k-nearest neighborhood algorithms. Apart from all the mentioned above, assembly learning algorithms such as boostings are implemented in our data and are proved to enhance the overall performance, especially random forest algorithm, which is commonly used in sound event detections.
The evaluation metric we use is AUPRC. We use this metric because our data is very imbalanced and we want to find the positive data samples. For convenience, we use the macro average AUPRC over all course classes to do evaluation. The following table contains the performance of all the classifiers we trained with the best parameters and feature sets. We noticed that AdaBoost and random forests make better predictions. It seems that in simple models it's less noisy and outperform other single models. Also, adding STC features did improve the results by informing what sounds we may expect to hear in a recording. This table contains the AUPRC for different feature combinations using random forest classifier. Notice that log-mail filter bank has better prediction. The reason might be that to obtain MFCCs, a discrete cosine transform is applied to the filter banks, which could hurt the future training. Lastly, we noticed that changing the window sizes and using dimension reduction techniques didn't improve the results.
For our project, we had the following conclusions. Feature dimension reduction methods like PCA and NMF do not aid classifiers if features' dimensions are already reduced. Also, the methods available to us in this course were not as effective as the deep methods like convolution neural networks applied by the groups in the actual challenge. But most importantly, spatiotemporal context features almost universally aid classifiers. Real-world impact comes from this finding since data unrelated to the audio itself can help aid classification.